Next, I want to introduce 3 different types of NEM switches in our device library with both volatile and non-volatile functionalities. For the volatile, we mean is that the switch will turn off when the activation voltage is removed, so they can be used for building these logic functions. In this group, we first have the 3-terminal NEM switch with drain source and gate, and these switches can be a straight replacement for transistors in the complementary style logic. And we also have the 4-terminal switches with an added body terminal, and this terminal is mechanically coupled with the source terminal through the dielectric plug. So when this switch is activated, the 2 beams will move together towards the drain, and this coupler actually can electrically isolate them. I will talk about the benefits for this configuration later in the slides. For the non-volatile NEM switch, that means the switch will retain its program state after the activation is removed. And in this group, we have the 7-terminal NEM switch with a semicircular beam attached to the source terminal. And this switch can actually be rotated into both clockwise direction and counterclockwise direction, depending on where you apply the activation voltage. And with this switch, we can build the non-volatile memory cells. So these are the 3 types of devices we use to build integrated NEM switch and NEM-based circuits. For each type, these are the microscale relays that has been developed and published previously. And we took this proven design and asked, how small can it go within the current fabrication limitations, and how much chip areas can be saved through the miniaturization? I want to share this optimized nanoscale design first, which are developed during my PhD study. Both the structural dimensions and the contact design have been largely optimized to adapt for the wafer-level integration approach. And if you compare the micro and nanoscale design, and if you look at the scale bars, you see that the nano design has been shrunk 5 to 10 times smaller than the microscale design. And for the microscale switch, the critical dimension is roughly 1 micrometers, and for the nanoscale, it's roughly 100 nanometers. So based on these nano designs, we developed the following 2 integration strategies. The first one is the NEM-first monolithic integration. So this integration approach can be divided into the foundry process, which has been done in the CMOS foundry, and then the post-foundry process in the university clean room. For this foundry process, this one is based on the ICP-P50G process finished by IMEC Belgium. And first, we have an SOI wafer, and then we pattern the NEM switch with step lithography in the CMOS foundry, and also do the dry etching on the silicon device layer. And next, we deposit the back-end-of-line dielectric and metal layers on top of the switch terminals. And finally, the aluminum pads are deposited on each of the terminals. Because the NEM switches are fabricated before the back-end-of-line is finished, so we call it a monolithic integration approach. And this is the NEM-first process. And until the end of the foundry step, there is no additional modification to the standard foundry process flow. And this is very important because in this way, we can maintain the manufacturing uniformity and yield, the reproducibility of the device, which are the main concerns of using NEM switches in real life. But still, the NEM switch cannot move after this last foundry step, so we added 2 post-foundry steps to make the functional devices. So first step is that we deposit a gold layer on the switch terminals. And second, we remove the box layer underneath the switch beam to set the structures free. In this platform, we first implement both volatile 3T NEM switches and non-volatile 7T NEM switches. So these are the implemented 3-terminal and 7-terminal switches. They are imaged after the contact metallization. And these red areas you see are the deposited gold layer, which we defined using a windowed lift-off process with sputtering. So gold was the natural choice at this early stage for us because it is readily available for us in the university clean room. It offers excellent conductivity, and also it is chemically resistant to the vapor HF release in the following step. So after the release etch, we characterize two different groups of 3T NEM switches first. This one is with only silicon contact without any metallization. And we also have this 3T switch with gold metallization layer. And to electrically mirror the switch, first we ground in the source terminal, and then we put a bias voltage on the drain terminal. And then we monitor the drain source current by sweeping the gate voltage from 0 to 10 volts. And for both groups, you see that both of them has a pull-in voltage around 5.6 to 5.7 volts. But for the silicon contact switch, where is depicted on the red line, it gets stuck immediately after the pull-in and cannot be reprogrammable again. But for the switch covered with gold, it has a stable pull-out at around 2 volts. So this is the fully integrated 3T silicon NEM switch in the foundry platform, and it has a very low pull-in voltage. But the volatile switch also only works for one volatile cycle before receiving the station failure. And this reliability is limited by the material choice, which is the soft gold contact, and also the structural fragility with the long switch beam that makes it susceptible to the out-of-plane bending during the release step. And for 17 NEM switch, we also characterize it with grounding the source terminal, and then we put a bias voltage on both drain terminals. For this configuration, we investigated 3 different groups with also blank silicon contact, and also 80 nanometers of gold metallization and 40 nanometers of gold. So similar to the 3T NEM switch, for the 70 with blank silicon contact, we also have it only programmed for one cycle, and then it gets stuck and cannot be reprogrammed again. But for both of the two groups with gold coverage, they are reprogrammable. But we also observe that with a thicker gold metallization layer, the switch tends to be more volatile. So for the 18 nanometers of gold covered switch, it becomes a volatile switch with both pull-in and pull-out. And with the 14 nanometers of gold coverage, the switch becomes a non-volatile switch, so it can be programmed to one direction and then store the program states, and only if you apply voltage on the opposite gate, it will be reprogrammed to the other direction and then store another state. So we say that the switch functionality is tunable by adjusting the metallized contact design. We further take this volatile NEM switch and did the cycling test where you see here. The volatile 70 switch finally managed 44 volatile cycles before we see the station failure. And this reliability is still limited by the gold contact. And on the same integration platform, we also implemented a 4-terminal NEM switch, which shares the same foundry process as the 3T and 70. So they are implemented on the same platform and next to each other. But I bring up this one separately because it has a slightly different post-foundry process. So first, after we retrieve the wafers from the foundry, we deposit a thin layer of aluminum oxide on the whole wafer. And this layer actually has two functionalities. First is the passivation layer to protect the backend of layers from the vapor HF etching. And then it is also an important component for the 4-terminal NEM switch as the dielectric bridge between the body and source terminals. So this bridge will mechanically couple the two beams together, but electrically isolate them. And the next step, we also deposit a gold contact layer on the switch tip, followed with the full release of the switch. So this is the implemented 4-terminal NEM switch, and you can see the allox plug and the gold contact here in the image. It has 4 terminals: the source, body, gate, and drain, and this switch can work as both 3T mode or the 4T mode. So if we activate it as a 3-terminal switch, and then we can ground both the source and body terminals, and we put a bias voltage on the drain terminal, and we sweep the gate voltage from 0 to 20 volts. And then you can see a pull-in voltage at around 15.8 volts, and then you can see a pull-out at around 12.7 volts. If you wanted to work as a real 40 switch, then we put the bias voltage on the body terminal. In this way, you can observe a significant reduction on the pull-in voltage from 15.8 volts to 7.8 volts when applying a bias voltage from 0 to minus 8 volts. And this result is consistent with the ideal prediction between the relationship between the pull-in voltage and the body bias. And the successful application of this analog dielectric clock also gives us good electrical isolation, and also to put the signal path values between the source and drain terminals to be decoupled from the activation control, which is between the gate and body terminals. And the lower pull-in voltage also gives us lower dynamic power consumption when you do the switch activation, and it gives us higher energy efficiency. Here is the cycling result for this 14 NEM switch, where the switch managed 20 volatile cycles before the station failure happened. And the reliability is limited by the gold contact.